right. Okay. So here's a picture from the board. I'll zoom in here. Whoops. Oh, all right. So here I've written out the solution formula, and yeah, this is all I have written down about the second homework. Homework, verify this. Um, so, and then in the um, notes that I wrote up for that day. Okay, so here I've had formula reproduced here, but I forgot to say include a homework statement with that. So okay, actually, I think what I'll do is, all right, if I close that and I go to the source file. Okay. I can fill in what needs to be put in there. Oh, something seems off here. Sorry, there seems to be a discrepancy between what I have written in the tech file versus the PDF. Oh, how can it be though? Because okay. Oh, I see what I did. Okay. Yeah, because here, like, the last thing in the document that you see is this right here, and here it is. And then I have end document, and then I have all this other stuff, and I'm not sure what that's doing here. Okay, so system, and that is equal to y of 0 at t equals 0. So if you were to plug in t equals 0 into this formula, then everything would simplify, and that is what would pop out. Okay. And I also want to make sure to include from the board here. You have various hints. EVAT, out of the integral, and use the fact that e to the at prime is a e to the at. Okay, so then you have everything else on the board. And I will update this in Canvas under September 21st. So, okay. Oh, right. And e to the a0 is the identity. All right. We go to homework 2.
So to clarify, like verifying that it's the solution of the y prime directly above it.
Yes. Okay. Dang it. Okay. Okay, yeah, that. Using fundamental theorem of calculus and all that good stuff. All right. So, all right, we're at it. So, any questions about prior homework problems, including this one? Okay. Alrighty. That reminds me, as you recall, it wasn't too long after this that I signed the third one. Was it the next day or? Okay. I want to take a look at what I have. Okay, that day, September 23rd, I was on the coast, so everything was typed in here. Okay, and I wrote down the homework problem in that case. So, okay, so every homework problem is teched up. Okay. All right. So I gotta post this after class. Okay. All right. And then I have okay. What I have here, I haven't put anything new in here yet. These are the notes from October 28th. Okay. And so I'm just reproducing them here. Okay. Just so you have everything in one place. So, okay, so here I have okay. And I think what I'll do here is I want to take out stuff that I don't actually need for today, since you can always go back to the October 28th document for it. Okay. So I'm gonna delete some stuff. Okay. Okay. See, I don't need that. Okay. All right, okay, this stuff I want. So we're dealing with this general linear ODE. Okay. All right. So I don't need this anymore. Okay, so all right, I just need to reorganize this stuff. Okay, so for this first order ODE, and we have our solution in this form, but then this part is Taylor expanded. Okay, so now I get everything in one page. Now I want to have everything as a system of ODEs now. That's really what this class has been about. Okay. Okay. So now we have sorry, all of this will come together in just a little bit. Okay. So solution of this system of ODEs that was arrived at last week, or actually the week before, is e to the at y of 0 plus this particular solution. Now, because this is a system of ODEs, I need to be careful about ordering. So now what we have here is a matrix function, and then b of t is a vector now. So this is a vector too. And so what we have here is a matrix vector product. So now I have a solution described in terms of these 5 functions. And just to have everything in one place, the general definition of a 5 functions is given here. And actually, I can use a 5 function here. This is phi 0 of at. And phi 0 of at is just a matrix exponential. Okay. Okay. So now I can get rid of the rest of the stuff. Okay. Sorry. Big mess to clean up, but now it's cleaned up. Okay. So we have a system of linear first order ODEs. Then here's the solution in terms of 5 functions. So what would happen is to evaluate these 5 functions, the matrix A times a scalar t is substituted in for w. Okay, so actually I can write this as 5w also. It's just e to the w. Stop that. Okay. So here we just have e to the at. And then, and the thing is, substituting at here for w, that's kind of a pain, but you don't need to use this formula. You can instead use this one to describe these higher order 5 functions that are included here. Okay. So I know I shouldn't have erased this, but all right. So that would be e to the at minus identity times A inverse, and that comes from phi 1 just of W is just e to W minus 1 over W. So here, W is replaced by matrix AT, and here we're dividing by W, but you don't divide by matrix, you multiply by its inverse. Okay. So all we have here is that you started with the exponential, you're subtracting off a certain number of terms, leading terms in its Taylor expansion, and then you're dividing by this, but that's the same as multiplying by the inverse. And the only matrix involved in any of this is AT, so it actually doesn't matter whether we put this on the left, as I've done here, or on the right, as it's done here. So there's no issue with of non-commutativity here, because every matrix in here commutes with each other. Okay. Now, so what is it? So what I want you to do with this information here. Okay. I'm going to give you a second order scalar ODE, y double prime plus p1 plus 4y is equal to t squared minus 5t plus 6 with initial conditions y of 0 equals 0, y prime of 0 is 0. And I'm also going to tell you what the solution is that I worked out just before class. Okay, so I have it in my notes here somewhere. Okay. All right, so 1/4 t squared minus 5/4 t plus 11 over 8. Okay, and you can verify that this satisfies both the ODE, ODE and the actually, wait a minute. You know what? This does not satisfy the initial conditions. Or I need to adapt the initial conditions to make sure it does satisfy. Okay. All right. All right, 11/8, and then okay, those are the initial conditions. That's still a solution. Okay. Now, so what is it I want you to do? Okay. First, rewrite the first order system, in this case of two equations. Y prime equals AY plus B. Okay. Okay. And then, so in other words, you figure out, well, what is A, what, and or B will be a function of T. What is that? A, B of T, and also vector of initial conditions, Y of 0. Okay, then, compute EVAT. By changing eigenvalues and eigenvectors. And I want to go back to, I'm looking back for the old notes. Let's see what would be most helpful for doing that. Certainly the matrix is going to be diagonalizable. Okay. Okay. Okay, that's not what I want here. There's some, I know there was some place, I'm trying to recall where, that something along these lines was worked out, like certain solution formulas given. Okay. Yes, this is what will. Okay, so it actually kind of builds on this problem, because what you have here is a formula for EVAT, and this formula is valid as long as the eigenvalues lambda 1 and lambda 2 are distinct, which in the case of this final problem, they are distinct, but they are also complex. That's why I had to do this third problem where you're working with this, but if lambda 1 lambda 2 are complex, then this whole thing is complex, and the goal is to make a solution formula real. So you can use this with the complex eigenvalues involved. Okay. Now, okay, so if I go back here, and all right, so that'll help with that. And then to express the solution, what I want you to do, since you'll have EDVAT, EDVAT, of course, is useful for evaluating any of these 5 functions of AT. So I want you to use this solution formula. Okay. Okay. Now the right-hand side here, since it's a second-degree polynomial, so your Taylor expansion would just come from the so 0 first and second derivatives of your polynomial. So the Taylor expansion will have a total of 3 terms for j equals 0, 1, 2. So that means you would need 5 functions, phi 0 over here, and then phi 1, phi 2, phi 3. Okay. Now, all right. So then, and what you'll find is that certain things simplify, and I wanted you to have the exact solution so that you know what you're supposed to get. And keep in mind, for your system of ODEs, since you're taking your second order ODE and rewriting it as a first order system, okay, so you're going to have this function as the first component, and then you'll have its time derivative as a second component. Okay. So after simplifying as best you can, this is what you should wind up with. Okay. Now, what I would suggest to reduce clutter since if you just use a formula from the notes to get EVAT, as I mentioned, it's going to be complex. But if you make it a real matrix, then everything else you do after that will be a lot cleaner. And this is the sort of thing that comes about from a third homework problem anyway. Okay. Okay, and that's it. So at least from this, you'll know if you're doing it right. Other questions? Quite bunch to the end. Okay. I guess really, I'm gonna rephrase this. Okay. There already is a formula for EVAT in terms of its eigenvalues, so you don't have to go trouble of, well, oh, sorry, I goofed. Since the eigenvalues are part of the solution formula, you do need the eigenvalues. The eigenvectors you don't need because in the solution formula, it's already known that these vectors, these columns of this matrix, are the eigenvectors. So I mean, yeah, you do need to compute the eigenvalues to get a formula EVAT that has specific numbers in it. But that's about it. And now you don't necessarily have to. I mean, you get a form for matrix A. You can compute its eigenvalues that way, or you can get it from a characteristic equation of this ODE. That doesn't matter to me. Or if you have a matrix, yeah, go ahead and use MATLAB's Eig to get the eigenvalues. I don't care. The point of this problem is using this form of solution in terms of 5 functions and doing that properly. So, now, for the 5 functions, for example, this one right here, okay, EVAT you'll get from the second part, you subtract identity. A inverse, you would use a formula for the inverse of a 2 by 2. And the higher order 5 functions, okay. like that, like phi 2 would have e to the at minus I minus identity minus at all times a to the minus 2. So you'd be taking a inverse and squaring it. Okay. Alrighty. Although there was something from the October 28 notes for expressing each phi function in terms of another, the recurrence relation. Okay. Well, yeah, this recurrence relation right here. So if I put that in terms of matrix form in the notes, but notice in the solution formula. Okay. Okay. Notice that we have phi j plus 1 of at times the same power of t out here. Don't forget that. So if I fill in a recurrence relation, that might simplify things a little bit. Okay, so keeping in mind what you'd have here, t to the j plus 1. Okay. It's equal to, okay. All right. EVAT. Oh, wait. Phi t minus 1 over j factorial identity times, here we have dividing by w, but that's the same as multiplying by at inverse. Okay. So here you have a inverse times 1 over t, but that's going to be canceling with one of the t's over here. So that simplifies to t to the j. Okay. And then you just have plain old a inverse. All right. So you might find that simpler. Okay. No. Okay, questions in the 3 minutes we have left.
I don't have a question on this yet, but I do need like a clarification on homework 1. Is that okay?
Okay. So we won't have any more class meetings. And okay. So then during the rest of the semester, you can just let me know if you have any questions. And as I've mentioned, in the other class that all 3 of you are in 560, I need to have everything in by like a Friday of finals week, which I believe is December 10th. just to be able to get everything graded in time. So good luck. Getting all the crap done I've dumped on you, and 2 or in some cases 3 classes. All right. So, okay. Well, see you in a half hour.